I took this picture. I'm standing on an island in the beautiful Manukau Harbour of Auckland, New Zealand, looking at the harbour heads. Behind me, there are mile-long causeways joining the island to the mainland that divide very large ponds. For decades, Auckland sent its sewerage to these ponds. I lived 3 miles away from where I took the picture. And it smelled just like you might expect. And during summer, we had midges like you can't believe. You'd get face sores of them. If you weren't careful, you'd get a mouthful of them. And our area was a bit of a laughing joke in the city. Then the city decided to put in a high-quality water treatment plant. They dug up all the muck and buried it. And today, it's New Zealand's biggest bird wetland. You can go there and see thousands of birds on some days, many different kinds of species. And the lesson here that we should clean up our muck before we eject it to the ecosphere, that there's huge advantage for protecting the planet in doing that. Now, I started my career thinking about designing catalysts to activate hydrogen peroxide to disinfect water so that we could get rid of the chlorinated disinfection byproducts. And today at Carnegie Mellon, I work with a brilliant group of graduate students with collaborators all around the world, particularly in endocrine disruption, and with a fabulous startup team to bring that vision, but an even more important one that I learned about later, because that plant in Auckland isn't really completely solving the problem. There are parts per billion to parts per trillion of at least 100 compounds that are disturbing aquatic life, wiping out fish species through mechanisms that are largely endocrine disruption in their nature. We think we have planet-saving catalysts. What do I mean? Well, this is a picture that just is telling you we have a very large molecule here, a peroxidase enzyme. These are at work in you right now, keeping you alive, doing all sorts of tasks, including breaking down chemicals. The business end is an iron atom that sits in the molecule there, and my job over 45 years ago was to think about how to shrink that thing down to a tiny thing that does the same chemistry. This chemistry is extremely efficient. We chemists don't have any really efficient peroxide activators other than the ones I'm going to tell you about today. So what we needed to do was that. We take the big blue ball and shrink it to less than 1% the size green cup. There's the iron atom sitting in it, and the mechanism's like this. The hydrogen peroxide, H2O2, the red ones are the oxygens, interact with the catalyst. They put an oxygen atom on the iron and they throw the water away. And then that molecule is vicious. And it will attack pollutants and break them up. And you have catalysis and you clean the water of the pollutants. Now, this has worked for a long time. How do we get there? So this is what I imagined in the Stanford Library. An iterative catalyst design protocol to get enzymatic efficiency. You imagine what the green cup is going to look like first. It has to get the right electronic structure at iron to produce this mechanism. You make it, you test it. Of course, if it works, you've solved the problem, but it didn't for a long time. But when it doesn't work, you don't walk away and say, oh, it didn't work. What you do is you go and analyze how it broke down, because the oxidizing catalyst is attacking in the green cup. And we got very good at finding out how things break down, and then you use your chemical intuition to change the catalyst to a new one where you've blocked the most sensitive site that you've found for decay. And then you make a new catalyst, and then you just go round and round that circle for a long time. And then 15 years later, someone came into my office. This was the catalyst. That's a molecular form of it. Put the data on my desk, and I thought, oh my God, it's worked. At that point, we spent 20 years playing around with the catalysts and seeing what they would do, changing their activity by putting groups here and there on them that really we had a million-fold difference in the reactivity that we could achieve, very precisely measured. We figured out how to measure the degradation rate of a functioning catalyst that had never been done before. And at the end of it, in 2013, I suddenly had a realization, because we could not separate the speed at which the catalyst would oxidize pollutants and the speed at which it would die. You made it go faster for pollutants, it would die faster, and the relationship was 1-to-1. And it meant that there had to be another mechanism, without going through all the details, for its decay. And so we went back to our design loop and made a new catalyst, slightly iterated, and suddenly took a giant quantum leap in the performance. We have had since 1995 the strongest, the most effective peroxide activating catalysts on the planet, across both chemistry and biology, and they've simply got better and better. We really understand how to control the aggression. We understand what the pH, when you're working in water, this is very important for catalysis. The pH really matters. We understand how that affects the reactivity. We can control the lifetime like you can't believe, which is very important when you're doing environmental applications. We understand and can somewhat control the rate, and the selectivity, whether a catalyst will attack this thing and not that thing. We learn about that, and there's tremendous value in the selectivity. So, for example, you can take a dye bath where you've put a fabric in the dye bath and you've stuck the dye on the fabric. Normally, you would pull that out and use a huge amount of water washing the excess dye off. You can leave it in the actual reactor. You can put tamyl peroxide in the solution. You will bleach all of the dye in the water, and you won't touch the dye at all that's bound to the fabric. This ends up as a huge saver of water and energy and things like that in the dyeing industry. So let's look at it in action. Here's some dyes. We're putting in the peroxide first. Turn on a stirrer, put in the catalyst, and you'll see what happens. So I call this sustainable ultra-dilute oxidation catalysis, or SUDOC. It's a new field, really. Only our catalysts are capable of this. You have teeny tiny quantities of the catalyst, low single-digit parts per billion, very small amounts of hydrogen peroxide, and you'll chase out parts per trillion, even, of pollutants. In the dyeing industry, we have 70+ billion tons of dye-contaminated water worldwide. We've worked with the Turkish industry. There isn't a dye that we can't handle easily and quickly. And so we think there are huge savings in energy and water, no colored rivers, et cetera, and we're very excited about that. But the micropollutants are the problem. The chemicals in water that are in the waters of all of our water treatment plants that are upsetting, destroying aquatic life at parts per trillion to parts per billion by the mechanism of endocrine disruption. This is where we're focused, but these catalysts do an extraordinary range of things, breaking things down and being useful in all sorts of areas. This is a paper we published, and title explains what we were talking about. And here we're making the pharmaceutical industry more sustainable, because actually, pharmaceutical industry doesn't test for endocrine disruption. Most of the most serious endocrine disruptors causing problems when you release that wastewater are pharmaceuticals. And we can break those down, and by doing that, we make the industry more sustainable. But you know, the sword of Damocles is hanging over me all the time. I'm not afraid of that. It should be there, because toxicity is so complicated. So I can't really say with 100% certainty my catalysts are safe. But what I do to have that not fall on me and skewer me is we do tests, and when we get positive results, that's another string holding it to the ceiling. We do lots of tests. And the way to think about our problem with chemistry is the following. This is performance language I've developed. This is the performance pie. Since corporate chemistry, as we know it, got going in the 1850s, We have commercialized chemicals because they have high technical performance and high cost performance. A chemical does something neat, people want it, somebody can make some money, you commercialize it. Every chemical has a health performance. If I give you a little bit of a chemical, you're different because there you are sitting there yourself and suddenly you have a chemical in you that you didn't have, you're different. It may not mean much, if it could be very toxic and kill you very quickly. If it's an endocrine disruptor, it could start altering your future children if you're going to have them in very unfortunate ways. Every chemical has an environmental performance. Similarly, I've told you a little about that. And every chemical has a fairness performance. Here's an example. In Puget Sound, the big cities put their wastewater into Puget Sound, and it's a kind of enclosed thing. The fish are swimming around in Puget Sound, and certain species of salmon, the Chinook, for example, stay close to shore. They're getting a dose of these micropollutants, and they're really miserable. The Native Americans live on those fish, and the fish are disappearing. By another mechanism, we're losing, this is Chinook, another mechanism, tire chemicals, we're losing coho salmon. We should deal with this. Testing is the answer. This is a group of people that got together and worked for 5 years, from 2008 till 2013, to figure out how you decide whether or not you've got an endocrine disruptor. It's the most marvelous group of brilliant, interdisciplinary people in this area. And I thought these things would feed into regulations. I thought the regulators would pick it up and start using the assays to protect the population. But we can't regulate. We really can't. But we can make money cleaning up problems. We love technological relief. And this is what I think our catalysts bring. So I'm actually looking to them more than I was looking to regulations before to try to solve part of the problems. Question is, what can you do? This is an incredibly serious problem. You're losing the ability to procreate if you're young. I think by the time my grandchildren I have 2 beautiful granddaughters. I think by the time they're of marrying age, they're going to have a sperm count test on the boyfriend if they want to have children before they marry. I think it's that serious. I think it's happening really fast. This is Europe. Its footprint's a little bit bigger, not quite 10% than America, but it's got more than twice the population and it's got less water. They've got a real problem with endocrine disruptors in the water. And if you look across from southern England at the bright lights there, that's the Netherlands. And the Netherlands are really the delta lands of great rivers, including the Rhine. They've got everybody's micropollutants from way upriver coming down, flowing through Netherlands, and they've got their own. So we're working with some wonderful Dutch investors and in a magnificent water centre in Leeuwarden to bring up this technology for water treatment in Europe. It's scalable. So, for example, if you take 8.4 kilograms of Tamil and you put 5 tons of hydrogen peroxide with it in 1 million tons of wastewater, you will do as well as any other technology. It's incredibly easy to use. That 1 million tons is the daily output of 6.7 million Europeans. That's 3 times the population of urban Paris and half the population of metropolitan Paris. This technology is really easy to apply. It's uniquely suited to both big and small plants. There is nothing else like that. We have some technologies for big plants, but Europe has 375,000 plants with less than 2,000 population equivalents, and our other technologies we have for micropollutants already are not going to work there. We think we have a fabulous future in treating water, and I can be push-up daisies happily if this takes off, and I'm going to keep going until it really does. Thank you.